Hello everyone and welcome to this one maths video on parametric integration, which is part of the P4 syllabus. So I want to start first by talking to you about deriving the formula for parametric integration. And so let's just have a look at when we normally integrate. We would say, well, we have a function y and we are integrating with respect to x between my upper and lower limit. So if I have this function here, then between a and b, I will integrate in order to find the area under the curve. Now what's different with parametric integration is, well, we're dealing with parametric equations, so we know that x is a function of t. We also know that y is a function of t. And so in order to deal with this, we want to be able to rewrite my integral formula in terms of these parametric equations. So we're simply going to say, well, I'm going to integrate a function which normally would be y, so g of t, and I'm going to multiply that by dx dt, and I'm integrating with respect to t because we have parametric equations. And so you'll notice that this very nicely is just our original equation or formula rewritten. So essentially I have the integral of y dx dt dt, and they cancel nicely to leave me with the integral of y dx. And so there we have it. We are going to use this formula in order to integrate our parametric equations. Of course, you can turn parametric equations back into a Cartesian equation where you have y as a function of x, but that's completely unnecessary. Okay, so let's have a look at a few examples here. So our first example tells us determine the area bound between x equals 0 and x equals 3 for the parametric equations x equals t squared and y equals t plus 1, where t is greater than 0. So I'm going to just write down the formula I want to use, y dx dt dt. And here I need to be careful. I need to change my limits. So whereas before I had between b and a, I now will have between t2 and t1. Okay, so I need to always remember to change the limits. So I want to find the area below this curve between where x is 0 and wherever x is equal to 3. So the first thing I'm going to do is I always start by finding my t values. So finding the corresponding t values for x0 and x equal to 3. So, and for that I'm obviously just going to use x equals t squared. So when x is equal to 0, then I have that t squared is equal to 0, and therefore t must be equal to 0. And when x is equal to 3, I have that t squared is equal to 3, and therefore t must be equal to root 3. I also always need to check my domain, and I notice that t must be greater than 0. And I suppose in this instance, because I am working with that exact point there, it's probably, this should be t greater or equal to 0. Okay, so my second step is that I'm going to now apply my formula. So when x is 0, t is 0, that's my lower limit. And when x is 3, t is root 3, that is my upper limit. I'm using y and y is equal to t plus 1. And I'm also using dx dt. So if x is equal to t squared, then dx dt is going to be equal to 2t. So I'm timesing by 2t, and I'm integrating with respect to t. So if I expand this, I get the integral between root 3 and 0 of 2t squared plus 2t dt, and that becomes 2t cubed over 3 plus 2t squared over 2, which is just 2 squared, between 3 and 0. Then I'm going to plug in root 3, and I'm going to get 2/3 times root 3 squared, which is 3, plus root 3 squared, which is another 3, subtract 0 when I plug that in, and that very nicely is going to give me, hang on, that's going to be 2t cubed. So that's actually 2t cubed divided by 3. So that's root 3 cubed there, which will give me 2 root 3. 2 root 3 plus 3 as my final answer. And that is a really simple example, first one, of how we integrate parametrically. Okay, let's have a look at another example. Determine the area bound between x equals 8 and x equals 0. For the parametric equations, x equals 8 minus t cubed and y equals t squared plus 3t. So, first thing I do always is find my t values. So here we go. When x is equal to 0, I will have that 8 minus t cubed is equal to 0, and therefore t cubed must be equal to 8, and therefore t is going to equal 2. And when x is equal to 8, I have that 8 minus t cubed is equal to 0, and therefore t cubed, is equal to 8, and therefore t cubed is equal to 0, which means t must be 0. Okay, so I noticed that my upper limit of 8, let's say that is there, and my lower limit of 0 corresponds to an upper limit now, a t value of 0, and a t value of 2. So it's very important that we keep the same order. Okay, so if before we had between 8 and 0, then for t, this is now going to become between 0 and 2. Don't swap it over so that you have the higher value at the top. It all depends on the corresponding t values. Okay, so now I'm going to solve this. So I will have the integral of y, which is t squared plus 3t, times by the derivative dx dt. So dx dt is going to be minus 3t squared times by minus 3t squared, and that's going to be between 0 and 2, or 2 and 0 dt. Okay, let's just simplify this. This is going to give me between 2 and 0, I'll have negative 3t to the 4 minus 9t cubed dt. So I'm just going to show you a really nice little card to have up your sleeve. Tricksy. I can, if I were to multiply, I can sort of swap these limits around so that I have the 2 in the top and the 0 below, as long as at the same time I'm multiplying everything by -1, and swap the limits. So that's a nice way for us to deal with the negatives here. So I'll get 3t to the 4 plus 9t cubed dt. Okay, so remember that trick, that's handy. If you multiply every term by -1 and swap the limits, you're going to get the same value as if you just do it as we've written it here. However, you won't have to deal with these negative signs. All right, so this, when I integrate it, will become 3t to the 5 over 5 plus 9t to the 4 over 4 between 2 and 0, which means I will have 3 times 32 over 5 plus 9 times 16 over 4, subtract 0, which very nicely will give me 276 over 5 for my area. Okay, right, let's move on to the very last example. Just going to move this down a little bit. Here we go. And example 3 says, find the exact shaded area of the curve given by x equals cos t and y equals sine t. And we're in radians, t is between pi and 0. So, as always, we are going to find our corresponding t values for here and for there. So I have that x is equal to cos t. So when x is 0, when x is equal to 0, I have that cos, sorry, not 0. When x is equal to 1 here, I have that cos t is equal to 1, which gives me, well, I know that the arc cos of 1 will be 0. And the second solution will be 2 pi, but we're just working between 0 and 2 pi. When x is equal to -1, then cos t is equal to -1. And between 0 and 2 pi, well, there's only one solution there, and that is when t is equal to pi. So that means for 1 will become 0 and -1 will become pi. So I go and solve my problem now. Before I would have had between -1 and 1, but this is now going to become between pi and 0. Pi and 0 of y. Remember, just to recap, my formula says y times dx dt dt. So y is sine t, and if x is equal to cos t, then I know that dx dt is equal to negative sine t. So it becomes sine t multiplied by negative sine t dt, which gives me between pi and 0 negative sine squared t dt. So again, I'm going to just apply my swap rule here between pi and 0 of positive sine squared t dt. So hopefully you recall that in order to integrate sine squared, I need to replace it by a double angle formula. In this case, cos of 2t. And cos of 2t is 1 minus 2 sine squared of t. And when I rearrange that, I get that sine squared of t is equal to 1/2 minus 1/2 cos 2t. So always just keep in the back of your mind that you'll have to use double angle formulas when you are integrating sine squared and cos squared. And there are others, of course, but okay, let's just deal with this. This is now going to between 0 and pi of 1/2 minus 1/2 cos 2t dt, which then very nicely integrates to become 1/2 t minus well, that's going to be divided by 2, so that's a quarter sine 2t, because cos 2t integrates to sine 2t, and then divide by 2 and times by half. Between pi and 0, which then, I always put this, will give me, if I plug in pi, I'm going to get pi by 2 minus 0. 2 pi, a 2 pi sine is 0, and that's going to be 0. Take away 0, which very nicely simplifies to pi by 2. And I don't know if anyone noticed, but this is a semicircle with a radius of 1. So we know the area is pi r squared, a radius is 1, pi r squared divided by 2, radius is 1. Therefore, it makes sense that the area here is pi by 2, which is exactly what we got. Okay, I hear from my lower 20 further maths class that what I should be saying at the end of my videos is smash that like button. So I'm aiming to build on my video resources this year. So if this is useful, smash that like button. Okay, thanks.